So today we are talking about finding the area above, below, between, beside the curve, okay? You're gonna learn how to find areas for all of these different things. And we kind of already started with the area above the x-axis, okay? We've already started with that, okay? Essentially, that's what you guys have, that's what we did the other day, okay? You're finding the area of the shaded region in between the curve and the x-axis. This is actually from the problem that we did on Tuesday, okay? Use the fundamental theorem of calculus to find the area between the curve and the x-axis. You guys know this already. That's the definite integral, so on and so forth, okay? To find the area above the curve implies that the curve goes below the x-axis. And we talked about it a little bit the other day. We're actually going to go into it a little bit more in detail. If a function is negative, so if your y's are negative and continuous on a particular interval from a to b, then the area is negative of the antiderivative of that respective function. Okay, so it's very important. Anytime you're below the x-axis, technically it's negative that area.
Also, it would be like, it would be negative f of x before you took it out.
No, essentially, yeah. Okay. And so basically you would still do the fundamental theorem of calculus, plug in the back, or do the antiderivative of the fundamental theorem of calculus, get this value, and then whatever this value is, you would do negative the value. And that would be your area for anything above the curve.
So is that why sometimes it was negative, a number was, it was because it was under the x-axis?
Mm-hmm.
Your best way to know is if both your values end up being negative when you do the fundamental theorem, that's most likely you're playing below or below the axis.
It'll make sense when we see it. Okay. All right. So let's look at an example. I think we're gonna look at two. I think we're looking at two examples of everything today. So the area bounded between the x-axis and the curve y equals x squared minus 2x. Now, gonna be like I said, for integration and derivatives, you gotta know your functions, right? You gotta know your other concepts. So first off, what does this function look like? It's a parabola, it's a quadratic that opens up. You can find your x-intercepts of your quadratic. How? So I have to set the function equal to 0. So if I do that, I can factor. What's the first thing you look for when you factor? GCF, which is? So this becomes x times x minus 2. So where are my two x-intercepts?
0 and 2.
0 and 2 are my two x-intercepts. Those actually happen to also be, since it opens up and it hits the x-axis at 0 and 2, you're looking for the area bounded between the x-axis and the curve. Essentially, you're looking for that. Question.
Oh, okay. Because at first I was like, oh, okay, now it makes sense.
So the entire area is below the curve. Below the x-axis. So when we find the area bounded between the x-axis and the curve, since it's below, it's negative the integral from 0 to 2 of our function. So again, we take the antiderivative, apply the fundamental theorem of calculus, and then whatever value we get, we negate it. So I want you guys to do that.
So that's the original. You can just plug in the original function and get the antiderivative of it, and then find the area using the fundamental theorem of calculus.
Mm-hmm. And then because the area is below, we have to remember that it's going to be negative.
Whoa, that's.
So what's the antiderivative?
I got 1/3 x, 2/3 power, 1 x squared.
I'm going to evaluate that from 0 to 2. I still got this negative on the outside. I'm not going to forget about it. Plug in my upper bound, so it's going to give me 8/3 minus 4. Again, I still got this negative on the outside. I'm not going to bother with 0 because when I plug it in, it goes away.
Yeah,
right? So what is 8/3 minus 4?
4/3.
Negative 4/3, but it being positive anyways.
But it becomes positive, so you get 4/3. Very good. Let's look at the next one. Okay. Find the total area of the region contained by y equals f of x and the x-axis for this particular function. Keyword here, regions. So that means it looks like it's probably going to be more than one region. And this can very well happen, all right? If it dips below the x, if part of the regions are above the x-axis, below the x-axis, you got to take that into consideration, okay? Because you're not going to be able to find the integral straight through once it crosses over the x-axis. So let me find my x-intercepts, okay? Set the function equal to 0. Is there a GCF?
Okay.
Can I factor the inside? What two numbers multiply to give me -3 that add together give me 2?
3.
And so my x-intercepts are at 0, -3, and +1. And using what we know from a prior class, x to the 3rd looks like,
It goes up, right? Yeah.
looks like this. That's exactly what this looks like. It's going to cross the x-axis at -3, 0, and 1. So cross, cross, cross. Does it matter how much is going to dip above and below? No, but you know that it follows in that cubic fashion where the end behaviors negative and then positive, okay? And so if this is -3, this is 0, and this is 1, the area of the regions down between the curve and the x-axis are going to be this region and this region. A region that's above the x-axis and a region that's below. So you got to do them separately
We
and
can't
add
add them together because they cross the x-axis.
because they cross the x-axis. Yep, exactly.
So if it didn't.
So-
then we would do it together.
Yeah, so let's say like your curve kind of did like this number,
Oop.
something like this. Yeah, then like everything's above the x-axis, so it's not going to change the area at all. So you actually can't go straight through as long as it doesn't dip.
This one we do both of the ways that we've been doing, like the.
Well, all we do is we just add a
Yeah.
negative sign.
Yeah.
Just the bounds.
All right.
Okay.
So we need to represent the left region, which is -3 to 0 of our function. Okay. And then we're gonna technically we would add it to the other region, but because it's below the x-axis, and you're gonna negate it. So technically it's a subtraction. So then I'm gonna subtract from 0 to 1 of the function again. And to save some time, I'm tired. Let's use our calculator. Because I showed you guys how to do it in your calculator, right? Let's see if y'all remember how to do it in your calculator. Exactly.
Big
brother's All right.
always here.
Here we go. So we're using our calculator for this one. Remember, we are subtracting because this particular area below the x-axis is negative. That's why we're subtracting instead of adding. Otherwise, we would add the different areas. So what was the answer that you guys got?
11.8.
11.8. If we're using 3 significant figures, what is that as a fraction? 71/6. Remember, answers are exact or rounded 3 significant figures. Can save you a rounding penalty potentially to use fraction. That's how you find the area above the curve, okay? For areas in between two functions, you need to determine which functions y values are greater on the respective interval, okay? So essentially, in these cases, to find area in between two curves, you essentially have to figure out, okay, which curve is bigger, which curve is on top, because, or which y values are larger than the other, because that's going to determine how you set up the integral to find the area between the two curves on an interval from A to B. So essentially, it is the top curve minus the bottom curve with the respective bounds. So here's an example. We're gonna find the area of the region enclosed by y equals x plus 2 and y equals x squared plus x minus 2. This one we're doing without our calculator. Then the second one we do, we're gonna use our calculator because we want to look at the graph for sure. So what does x plus 2 look like?
So y-intercept at 2.
Y-intercept at 2.
And then going up 1 to the side.
Yeah, right. 6 level 1.
So this is what x plus 2 is. Now what about x squared plus x minus 2? What does that look like?
So up and then
I have a y-intercept at -2.
It's like up 1 over 1, up 3.
Oh, but it's at the that's from the vertex,
yeah, but those the
not the y-intercept.
Mm,
So the words.
So you can either find the vertex of the quadratic and do it using the pattern, or you can find your x-intercepts.
Oh.
And I remember we're just trying to get a sketch to see which curve is on top.
2 and 1.
-2 and 1 are my x-intercepts. You are correct.
Yes.
So -2, the same point where the line intersects, and +1. So the vertex is actually -1/2. Roughly. Essentially, we just want to see which curve is on top and which curve is on the bottom. And as we can see, the area in between the two curves is going to be this area right here. Which curve is on the top?
Yeah, x plus 2 is on top.
X plus 2 is on top. It has the larger y values. And then the quadratics on the bottom.
Now it's fun to meet up, right?
And we do need to find a place where they intersect. Well, we already know one of them is at -2, but how do I find the other intersection point?
It's the negative equal.
Very good. So that's x plus 2.
X squared equals 4.
X squared is equal, x squared minus 4. X is equal to, wow, sorry.
Are you okay?
Like I'm struggling, I'm writing and I'm hearing and I'm trying to repeat, but
Yeah,
it's not
I'm not.
processing all together.
Maybe.
What is the other x intercept?
2.
Or the other intersection point? It's +2, because it'll be plus or minus. Doesn't matter. I just need the x value.
Okay. Think about this for a second.
So the integral from -2 to 2, I do the top curve minus the bottom curve. Top curve is x plus 2. I need to minus the bottom curve, x squared plus x minus 2.
And then you can split it up.
No, you don't want to split it up.
We combine like terms.
Combine like terms.
Oh, yeah.
So this becomes -x squared
Minus 4. No, sorry, plus 4.
plus 4.
It's the same. It's like how.
And then I take the antiderivative and apply the fundamental theorem of calculus.
Negative 4.
Hmm?
Oh, yeah, I was asking you to put the down on the thing.
Yes. So as we are working through the final computations of the area between the two regions, remember we wanted to find which curve was on the top, which curve was on the bottom, because that's exactly how we plug it into our integral, top minus bottom. X plus 2 is my top curve, x squared plus x minus 2 is my bottom curve. Combine like terms, I apply my bounds, the points where they intersect that encloses in that region. And our final answer is what?
Okay, 32 over 3. But I don't know if that's right.
32 over 3. Could I get some confirmation?
Cause the 8 thirds come together and be negative 16 and 3.
3 plus 16.
Yes.
Yeah, it'd be 32. That's correct. And I was waiting for confirmation too.
I say things, and you're right, wrong. I am wrong.
This one we're gonna do using our calculator. All right, we wanna find the total area of the regions by those two functions. I got a cubic and I got a quadratic.
Oh. I was over here like, oh, okay. You had like a revelation there.
Okay. Now remember, we're graphing this because it really and truly kind of just want to see we need to see which curve's on top, which curve's on the bottom.
Yes, we do. You're right about that.
Yeah. That's weird.
Cubic functions.
Ooh.
I need to change my windows.
So this is interesting. We have two regions, okay? I'm gonna sketch it out over here.
Oh, I don't like that. Ooh.
Roughly. Right, I have this region here, and then I have this region here. What's the difference between those two regions?
One of
One's
them's all
under.
positive.
And one's over.
One's what?
Like one's, okay, so the bottom and the top curve switch. So it's like the first one, it'll be the top one, and then the second, on the second reading.
We have to do 2 antiderivatives because.
Yep, we sure do. We gotta do 2 antiderivatives here because it changes which curve is on the top through those different regions. Okay, so for region 1, it's the cubic function on top and the quadratic on the bottom. But for region 2, it's the quadratic on top and the cubic on the bottom. So we can kind of set this up a little bit already. So I have the integral from sunbound to sunbound of the cubic function minus the quadratic function, and make sure you subtract the entire quadratic function. Then you need to add it for region 2. For region 2, the quadratic's on top, and then the cubic is on the bottom. I'm putting these expressions in parentheses because I have to distribute over the negative. The only thing I'm missing here is what?
Intersection.
My bounds, which are technically my intersection points. I have an intersection point here, here, and here, roughly on my sketch. But I can find it more specifically using my calculator.
Oh, yeah.
I have a zero.
So 0 is one of them?
You're, I think there is an intersection 0, 0.
So there's not 0, 0, but
Yeah. This is,
0, 3.
yeah.
So I have an intersection point at 0. So that's the upper bound of my first integral and my lower bound of my second integral.
The left one's -2.
There's one at. Wait, what?
And there's one at 3.
There's
Yeah.
one at, yeah, white.
That's what I'm thinking.
Okay,
It's like a really small number.
can I get some confirmation on these intersection points?
My calculator said so.
It's almost a 0.
So remember, you find the intersection points by doing second trace. Option 5, especially if you're able to use your calculator. So if you're trying to find a closer intersection point, you want to move the cursor that way. And yes, it is 3 for the upper bound of the second integral, and then probably -2 for the other one. So find my antiderivative, plug it into your calculator, and give me my area between of my regions, the total area. So the area is going to be what again?
21.1.
21.1, or what's that as a fraction?
253/12.
There we go.
Oh, wait.
So that's how you find the area between two curves. Be careful, okay? Because this can get tricky, all right? Especially if you're given maybe one curve or maybe you're given two curves and like where that shaded region is. So just be careful to make sure you identify those regions correctly, especially if they're split. Last thing we'll talk about today is how to find the area between a curve and the y-axis. So far, we've seen how to find the area between a curve and the x-axis and between each other. However, if a function is invertible, meaning that its inverse is function, then we can find the area between the curve and the y-axis. How it essentially works is that you basically rewrite the function solving for x instead of y, and then you use the bounds along the y-axis or the restrictions of the y-axis as your bounds, and then the function in terms of y. If it's to the right of the y-axis, the area is positive, but if it's to the left of the x-axis, the area is negative. All right?
So you would, if you just give you a function y equals whatever. You would
Yeah.
Switch to x and y, find the inverse, and then use.
Have to find the inverse, or can you just leave it?
Well, what you would do is you would technically solve for x, which is
So
essentially
switch to
finding the
y.
inverse, but you're putting it in terms of y. So then that way you can use your bounds as y. Because normally our interval has been on the x-axis, but since we're being restricted with the y-axis, you want the function in terms of y instead of x, because your bounds are in terms of y instead of x. So you'll see it in a second.
Okay. So
But-
you wouldn't find the inverse, you wouldn't solve for the inverse, you would just switch to the x and y.
You would solve for x in the function. You'll see it. You'll see it. All right. So a few things again to take away. If you are finding the area between a curve and the y-axis, if the area is to the right, it's positive. The area is to the left is negative. Same thing above and below. So we're gonna look at this example, and I want to have you guys try one on your own. Then we'll be done for the day. We're gonna find the area between the curve f of x is equal to the square root of x minus 1 and the y-axis between y equals 1 and y equals 2. And also for the function 2 minus x cubed, the y-axis between 3 and 10 on the y-axis.
Why is it called between the curves if it's only between?
So we have the square root of x minus 1. Just to let you guys know, a little quick sketch. That looks like that. You are finding the area between 1 and 2. So essentially what you're looking for is this area right here. That's essentially what you're looking for. So since our bounds now are between 1 and 2, and those are bounds that are on the y-axis, you need the function in terms of y. Right now, the function is in terms of x. So what we need to do is we need to take our function y equals the square root of x minus 1, and we need to solve for x. So then that way we can get the function in terms of y.
Oh, finally, you do
So-
something easy.
All right, how do we do this?
Or everything.
No, you square it.
Square everything.
I mean, square, look.
And then?
I'll subtract over -1. I mean, add over -1.
So the function that I'm going to take the antiderivative of is going to be y squared plus 1, and it's not going to be dx, it's going to be dy. And then we just integrate it like we normally would. What's the antiderivative of y squared?
1/3 y to the third power plus 1.
And I'm going to evaluate that from 1 to 2. So it's going to be 8/3 plus 2 minus 1/3 plus 1. Let's see, that's 7/3 plus 1. So 10/3. Confirmation.
Yeah, sure.
Sure.
Similarly over here with this one. I have 2 minus x to the third. I'm bounding it between the y-axis and y equals 3 and y equals 10. This is the cubic that has a y-intercept at 2. So essentially what you're looking for is this area right here. What do you see?
What am I supposed to say?
On the picture, huh?
Well, I mean,
That is, you're gonna have to put the negative?
I gotta put the negative because it's on
because
the
it's on the
left side. Okay,
yeah.
so be careful. It's the same concept of if you were to dip below the x-axis, that area is negative. So it's negative the integral from 3 to 10 of your function with respect to y. Right now it's with respect to x. So if I work this function out, and solve for x, how would I do that?
2 minus y, the cube root minus y.
So it'd be 2 minus y is equal x to the third.
You get the cube root of it?
So I have the cube root. So this becomes the cube root of 2 minus y dy. That's the same thing as saying 2 minus y to the what power?
1/3.
And there were some linear
Yeah.
factor rules that you would use here for this example. So I want you guys to take a moment, find the antiderivative, plug in the bounds, and give me a value. So it's 1 over a times 1 over n plus 1 times the linear factor and the n plus 1. That's how you do these. So the antiderivative of this would be -1, because that's the value of a. All right, so it's in front of the it's the leading coefficient. So it'll be -1 times 1 over n plus 1. Well, n plus 1 is 4/3. So 1 over 4/3 will be 3/4. Then you have your linear factor raised to the n plus 1, which is 4/3. And I'm going to evaluate that from 10 to 3. This negative came from 1 over a. I still have a negative in the front. So I'm going to keep that in mind as I'm still doing the evaluating of the limits. So this is going to be -3/4 times -8 to the 4/3, which is the same thing as taking the cube root of -8 to the 4th power. Then I'm going to minus -3/4 the cube root of -1 to the 4th power. Again, there's still a negative out there. What's the cube root of -8? What's -2 to the 4th power?
Oh, you can do it like that?
Yes, you can always take the cube root first and then apply the power.
Goodness, okay, that explains so much. That is.
So then that becomes 16.
Yes.
Then minus, we got -3/4. What's the cube root of -1? To the 4th power? So that just turns into 3/4. Again, there's still that negative out here. Can't forget about that. 4 divided by 6, 16 divided by 4 is 4. So this becomes -12 plus 3/4. Again, that negative is still out there. So this turns into -45 over 4, but there's still that negative there. So 2 negatives make a positive. So my final area is 45 over 4. And that's how you do it between the y-axis. I feel like it's gonna be the algebra that gets y'all, not the setup. It's gonna be the algebra that gets y'all.
Always.
All right,
Never fails.
we're gonna look at one more problem.
We'll have the setup fine, and then we'll just like struggle to do basic math.
Well, actually, we'll save this for the do now for tomorrow. But so let's recap. Let's recap everything that we've done so far today. You guys already know how to find the area in between, below the curve, okay? That's using the fundamental theorem of calculus
Yes,
with the bounds.
we know that.
Above the curve, we have to remember that it's a negative on the outside. Between two curves, you got to figure out which curve is the top function and which one's the bottom function, because then you subtract. Being careful that if at any point in time, maybe the function that was originally on top is not on top for the entire interval. So be aware of that. And then lastly, between the y-axis, if it's to the right of the y-axis, it's positive, to the left is negative, and we do it with respect to y. So make sure that you solve your functions for y, so then that way you can find the antiderivative.